Hello everyone, this is Jorge Chavez speaking. I'm a graduated student from Francisco de Paula Santander University. My advisors are the Professor Luis Vera from Francisco de Paula Santander University and the Professors Leonel Cancino and Amir Martins from University Federal of Santa Catarina. Our research is titled The Ahmed Body's External Aerodynamics at 25 grade Slant Angle Rear Surface, a numerical analysis using CFD. This is our agenda. Item 1, Introduction. Item 2, Methodology. Item 3, Results and Discussion. Item 4, Conclusions. Let's begin with the introduction. Vehicle aerodynamics has been developed in order to determine the relationship between the airflow around and through the flow field. The airflow that passes through the engine compartment is completely dependent on the flow around the vehicle. The external flow generates forces and moments on the vehicle, which determine the car's performance and directional stability. Another purpose of vehicle aerodynamics is to avoid water and dirt on the windows and the surface of the lights. Additionally, to minimize any aeroacoustic effect that can rise because of the movement of the car. On the other hand, to provide the airflow for the cooling of the engine and passenger compartment, among other functions. Computational techniques such as computational fluid dynamics, better known as CFD, are used to assess the aerodynamics performance of a vehicle in relation to drag, lift, moments, pressure center, among others. Another great advantage of CFD is that the results are obtained in a relatively short time. Therefore, the objective of this study is to analyze through a CFD tool the external aerodynamics of the Ahmed body reference geometry. This geometry greatly represents the vortices and the airflow generated around a real vehicle. Different aerodynamics performance can be found according to the angle of the inclined surface at the rear of the Ahmed body reference geometry. For the development of this study was select the angle of 25 grade in the rear inclined surface, which represents the vortices that are generated in a fastback type vehicle. Methodology. The Ahmed body reference geometry is composed by three parts. The front section, which is round to keep the flow attached to the surface. The central section, represented by a rectangular box with sharp edge, and the back inclined surface, where the flow shows different behaviors according to the angle of inclination. Figure 1 shows the geometric shape and main dimensions for the slant angle of 25 grades, focus of this work. Despite the considerable deviation of this geometry from the usual vehicles, the generic geometry represents the basic aerodynamics properties of a real vehicle, especially at the rear area. A rectangular section was designed and used as the test section of the virtual wind tunnel. On the other hand, taking advantage of the symmetry of the Ahmed body reference geometry, only the half of the body was used to develop the simulations. Following the recommendation given by Agarwal, the frontal distance conformed from the velocity inlet to the frontal area of the Ahmed geometry has 3 times the length of the geometry. This distance allows the development of the flow before it reaches the geometry's surface. Figure 2a shows the main dimensions of the virtual test section of the wind tunnel. Using the refinement strategy based on volumes of influence, which allows to combine different types of elements within a mesh and directly control the size of the cells, 3 volumes were introduced as shown in figure 2b. The first, the cardbox influence geometry, was located in the entire region surrounding the surface of the Ahmed geometry. The second one was the underbody box, which was positioned between the road and the region of the ground surface of the geometry, to obtain the main features around the steels and the rear area, shown at the top right of figure 2b, and to capture accurately The free field in the way area, a tear influence geometry called wave box, was placed before the inclined surface in order to capture the separation and recirculation area properly, as shown at the bottom of figure 2b. This strategy was essential because it ensured that the mesh will properly resolve the effects of velocity, pressure, and boundary layer around the surface. Now, we're gonna talk about the results. The air velocity of 40 meters per second was selected for all the numerical simulation in this work, which means that this velocity is below Mach 0.3. Consequently, the effects of compressibility can be ignored. The simulation of this project were developed with four turbulence models: realizable K epsilon, RNG K epsilon, standard K omega, and Reynolds strength models. The first three models have two transport equations, while the Reynolds stress model had seven transport equations. Each one of these models have different configurations to predict the behavior of the flows. Table 2 shows the difference percentage between the drag coefficient of the simulations as well as the value of the path length of the computational domain, the length of the wake box, and the total number of the elements for each case are presented. Table 2 also shows results that the drag coefficient after the simulation of 4L had a convergence tendency. However, for the value of 12L, a higher value was observed compared to the previous ones. One of the hypotheses to explain this small discrepancy is the low number of elements used for this configuration, being around 2.5 million of elements. Therefore, to determine and analyze this behavior, the mesh independence study was executed on the computational domain length of 12L. Figure 4 shows the trend of both the independence tests performed in this work. Please note that on Figure 4a, the x-axis represents the rear length in meters, and Figure 4b, the x-axis represents the number of elements of each mesh progressively reducing the mesh size. As after the fourth case of refinement, the difference between the drag coefficient values shown a percentage lower than 1%. Reaching this state can be considered that the mesh will reproduce results with no dependency of the mesh size, since the value of 5.4 million of elements show a difference of only 0.6% with respect to the previous value. It was selected for all numerical simulations in order to compare numerical results of this work to the experimental data available at literature. Table 4 shows the percentage difference between the experimental to numerical results. It can be observed that the realizable K-epsilon turbulence model has the lowest difference to predict the experimental drag value, with only 3.90% of difference. At the same time, it was determined that the other turbulence model tests in this work also adequately captured the total drag value. The maximum difference was of 6.33%. This indicates that the mesh quality as well as the setup used in this work are adequate to determine the external aerodynamics of the surfaces of the geometry in terms of drag. To validate the lift, the experimental research conducted by Mail was used to validate the lift coefficients. In this investigation, the generic Ahmed value was used with the original dimensions, with an angle of inclination of 25 degrees and air velocity of 40 meters per second. The value of the lift coefficient obtained was equal to 0.345. Table 4 represents the results of the lift coefficient for the four turbulence model and the percentage difference against the experimental value. The smallest difference obtained was of 2.28%, while the largest difference was 8.88%. This means that while some turbulence models are suitable for capturing the drag, others can barely capture the lift. Apart from this, the positive value of the lift coefficient for the 25 grades slant angle indicates that the flow between the ground and the Ahmed body floor has low velocity. As a result, there is a higher pressure at the bottom than at the top, which generates a positive lift force. The realizable K-epsilon model resolves in a better way the turbulent viscosity. At the same time, it has new transport equation for the dissipation rate and satisfies certain mathematical constraints on the Reynolds stresses, in agreement with the physics of the turbulence flows. For this reason, it was observed that the realizable K-epsilon model predicts the drag coefficient accurately. On the other hand, the Reynolds stress model is one of the most elaborate types of turbulence models, solving 7 transport equations for 3-day cases. It was also the most computationally time consuming. Thanks to its great ability to predict more accurately the different pressure gradients around flat surface and streamlines, it was observed that for Ahmed reference body, this turbulence model showed greater proximity to the experimentally calculated lift value. Hucho, in his research, showed schematically the flow field around the Ahmed body reference geometry. The numerical simulations performed in this work were able to capture the main vortex for 25 grades slant angle as observed comparing figure 5a and figures 5b. The planes P1, P2, P3, and P4 in figure 5d also show the fluid evolution in the wave region and will be used for data analysis on figure sheets. Figure sheets compare the numerical and experimental behavior of the fluid field in the wave region. For the fourth plane of figure 5d, it can be observed a good agreement in the flow field shape, as well as in the flow evolution along the wave region. Comparing figures 5d and 6, it is possible to see the flow evolution in the airflow direction through the wake. With the intention of validating the velocity field around the surfaces and in the wave region, the experimental research developed by Linhart was used. In that work, 8 velocity lines were created on the entire computational domain, which 5 velocity lines are over the surface of the geometry as shown in the figure 7, and 3 velocity lines in the region of the wave as shown in this figure. In order to make a comparison of the velocity distribution in previous planes observed, the same lines were created from the numerical result of this work and plotted as shown in figure 7, where the colored lines represent the numerical results and the colored dots represent the experimental results. Through this comparison, it was proven that the numerical results obtained truly represent the flow field around Ahmed's body reference. Now, let's see the conclusion of this research. The first conclusion is that the relevant data related to drag and lift was obtained and well compared to experimental results previously published in the literature. The numerical procedures are set up, computational domain length, and mesh size were then correctly chosen, and the small difference for drag and lift coefficient found in this work can support that. Our second conclusion is that the numerical results show that the realizable K-epsilon turbulence model well approximates the drag with 3.9% difference to experimental results, and the Reynolds stress model better fits the lift with 2.8% difference to experimental results. Finally, the velocity profiles on the wake region were then plotted and compared to experimental results, obtaining good agreement in function of the numerical to experimental agreement. It was possible to access to relevancy in the use of CFD for aerodynamics analysis when adequate choices are done in setup and match options. We invite you to consult the complete paper for better information about our research. Thank you very much.